Hi everyone, in this video I'm continuing to work through question 14 part A of the 2020 Baulkham Hills Extension 1 trial exam. In this video I'm focusing on part 3, so if you haven't already seen my videos on part 1 and part 2, have a look, I'll provide some links. Part 3 tells us to let angle COD equal theta as shown in the diagram, and then they want us to show that vector A dot vector F is equal to negative vector C dot vector D. And it's important to note these dots here are the dot product, the vector dot product of these vectors, as opposed to say just, normal multiplication. So yeah, let's take a look. Again, I've recreated the diagram just to remove a lot of the noise that we encountered on the prior parts and just focus in on what we really need to look at for this question. Now, as I mentioned, these are dot products, so it might be helpful just to note what is the rule for vector dot products. And if I just draw a very simple, we've got a vector here, maybe I'll call that vector u, and another vector here, I'll call that vector v. And we've got the angle between, maybe I'll use alpha, just because we've already got a theta in our real question. The dot product says that u vector dot product v vector, that can be written as the magnitude of u vector times the magnitude of v vector, and that's just normal multiplication there, times the cos of the angle between them. So in our case, that's the angle between them is alpha. And so that's kind of the rule that we're going to make use of to draw this conclusion about the dot products between the various vectors we're dealing with. Now, if I wanted to say, think about vector A and vector F, which is what we've got over here, well, I need to know the angle between them. We're given theta as the angle over here, but I'd like the angle between A and F so that I can start thinking about their dot product and then, see where I get to. So maybe as a step one, we know, we're told that these are squares, so we know that these angles are right angles. So actually, knowing that this is a 360 revolution, it's not too hard to find what AOF should be. We can say, maybe we can just write, since angle COD equals theta and ABCO and ODEF are squares, then we can say that 90 degrees plus theta plus 90 degrees, so that's 90 theta 90 plus angle AOF, that's all going to be 360 degrees. So if I bring these two 90s over, it'll be 360 minus 180, so we'll end up with theta plus angle AOF is equal to 180 degrees, because 360 minus 180 is 180. And then we want angle AOF by itself, and so I'll bring the theta over, so it's just 180 degrees minus theta. So that's the angle that we're going to throw into our dot product rule when thinking about the dot product of these two vectors. So let's start. I think if we can start with these two vectors, we'll get to our right-hand side, because these are 2a vector, 2f vector. And then I guess the task becomes simplifying it to show that with our dot product rule, we end up over here. So yeah, let's take a look. We can say, so OA vector, maybe I'll just write it in the letters first before I throw in our vectors. So we can say by this dot product rule, the dot product of OA vector with OF vector, that dot product will be the magnitude of OA vector times the magnitude of OF vector times the cosine of the angle between them, which we've just worked out is 180 minus theta. 180 degrees minus theta. Now, just as a little side note, we're going to want to simplify this. So actually, if we make use of our rule about cos A minus B being equal to cos A cos B plus sine A sine B, well, just as a little side calc, we can say here A would be 180, so cos 180 cos theta plus sine 180 sine theta. And if we think about our 180s, I'll just get my calculator. So the cosine of 180 is just -1, so that's going to be negative times cos theta. And the sine of 180 is 0, so that just drops off. So actually we can just write negative cos theta in here when we're simplifying. So let's do that. Let's now throw in what we know our definitions are of OA and OF. So we can say therefore vector OA, which is 2A vector, dot product vector OF, which is 2F vector, will be equal to the magnitude of 2A vector times the magnitude of 2F vector times negative the cosine of theta, since that's what we worked out over here. So all of these 2's, these just simple numbers, they can all, well, at least over here for sure, we can just multiply them out. So this will just be end up being 4 times the A vector dot product F vector. And what's that going to be equal to? Well, let's just write this out a bit more cleanly. It's going to be negative of the magnitude of 2A vector times the magnitude of 2F vector times the cosine of theta. Now, let's think about what we've really got here, because theta in this world is the angle between these two vectors, and we've got a cos theta, which is the cosine of the angle between two vectors. Now, remembering that each of these are squares, well, we know with squares that the length of the sides are all the same. So if we're thinking about magnitudes, the magnitude of 2A vector and the magnitude of 2C vector, they're the same. And the magnitude of 2F vector and the magnitude of 2D vector are also the same, because they're lines in a square. So we can actually say, well, this is equal to, might just need to come up a little bit just so we don't lose it off the page. It's going to be equal to negative, instead of 2A vector, I want to write 2C vector so I can get things back in this dot product form. So I'm going to say the magnitude of 2C vector times the magnitude, and instead of 2F vector, I'm going to write 2D vector, which again I can do because these are lines of a square, so their magnitude is the same. Sure, their direction may be different, but we're only thinking about their magnitude right now. And then we've got our cos theta. Now, this bit here is the right-hand side of our dot product rule. So we can now insert the left-hand side of our dot product rule, and that's totally valid. Now, I might have to turn over at this point, so let's just keep going. So we'll say, therefore, 4 times A vector dot product F vector is equal to, and we have our negative, can't forget that. And now it's really this, if we convert it back to the left-hand side, would be 2C vector dot product 2D vector. So we'll say negative 2C vector dot product 2D vector. And just like we did before, we can bring these 2's out, so that's going to be negative 4C vector dot product D vector. These 4's will cancel, and so therefore we can conclude that A dot vector, So A vector dot F vector is equal to negative C vector dot product D vector. And if we look at that, and if we look at what we were being asked to show, that is what we were being asked to show. So that is as required.
Panic boom!
All right, that's how you tackle that question. So I guess the element of vector knowledge that we've really been tested on here is our knowledge of the dot product rule. And actually you can see that we've had to both apply the dot product rule by taking the left-hand side and expanding it into the right-hand side. That's how we got from here to here. And then we had to, I guess, notice that we're dealing with squares to then allow us to use the dot product rule to come back, but just with two different vectors. And that's how we were able to show this result that we eventually were being asked to show. So, yeah, quite a tough one actually, because I think you had to make use of a lot of stuff. You had to know your vector dot product rule quite well, particularly knowing that for these vectors, it's this angle here. I could see a lot of students making the mistake of just throwing in a cos theta right away. Now actually, if you wanted, you could have started with 2C and D and started with your cos theta right away. And then again, with equally careful work, you hopefully would have still got to the right outcome. For me, I just started with the A and F vectors, only because really I thought naturally let's just start with the left-hand side. But there's no reason why you couldn't start with the right-hand side and work towards the left. I think you'd still get there. So yeah, there you have it for part 3. Hopefully all of that made sense and you followed along with that. So in the next video, I'm going to work through the final part, part 4 of this question. All right, tick boom.